I will try to tell you a little bit about viscosity solutions, and I was asked to start very elementary. So forgive me if it is too elementary for you. And in fact, if it is, you have to tell me, and then I will go a little bit faster. I mean, we know classical solutions in partial differential equations. We know weak solutions in partial differential equations. And for the last 20, 30 years, there has been a development of another idea of solutions, so-called viscosity solutions. Why does one need viscosity solutions? And for me, the motivation to study viscosity solutions comes from a physical phenomenon. I guess you know what an hourglass is. It is a glass that has this shape. In the middle there is a thin passage. And you have sand up here, and the sand is running down, and it forms a pile down here. And in fact, I mean, every child that starts to play in the sandbox does experiments in continuum mechanics with sand. And say, if we have sort of a point source of sand that is falling on the ground, a conical heap will start to build. Because when the slope here is too high, then the sand will run down the slope. And, well, if you have a second source, a second slope will start to grow. And there was a mathematician by the name of Gunnar Aronsson. In Linköping in Sweden in the late 1960s, he studied this phenomenon, and in particular he studied what happens when these two hills merge. Because then somehow some sand is running here, some sand is running there. You expect something like this. Now this does not happen in one dimension, in fact it happens in two dimensions. And what is a natural description for the differential equation that comes with it? Well, we expect the sand to have constant slope when we go uphill. And this means that the second derivative in direction of gradient u should be constant. So this means that I take the Hessian matrix of second derivatives and I multiply it from both sides with a gradient. And in two dimensions, so this is uxx, uxy, uyx, uyy, multiplied with ux, uy, and then again multiplied with ux, uy. This should be equal to 0. So when you multiply this out, this is ux squared uxx plus, assuming that the solution is C2, then uxy is equal to uyx plus 2ux uy. Uxy plus uy squared uyy equal to 0. Okay, so now that's an equation that has second derivatives of u. And it is reminiscent of an equation which has variable coefficients, aij times d2u dxi dxj. When this coefficient matrix is the identity matrix, then we get the Laplace operator. So here we have the aij equal to uxi, uxa, uxj. for aij equal to delta ij, that is 1 if I is equal to j, and 0 if I is not equal to j, then we get Laplacian u equal to 0. That's uxx plus uyy equal to 0. Now this operator here, well, what do we expect of an elliptic operator? A linear elliptic operator has the property, so the operator A defined by the aij is elliptic if the sum aij cj is greater or equal to some constant, let me call this ellipticity constant c0, times the modulus of c squared. And for the identity matrix, this is the case. For this matrix, it is not the case. In fact, suppose we have some function given by its level set. So here say u is equal to 0, and here u is equal to 1, and here u is equal to 1/2. Then we know that here the gradient is pointing from here to there, and over here it is going this way. The gradient of u is a particular direction. So what this operator tells us is the second derivative of u in direction of the gradient multiplied with gradient u squared. So. And this equation, in fact, is called the infinity Laplacian of u. So let me define the infinity Laplacian of u. That is just the sum d2u uxij uxi uxj. Now, Aronson was looking for explicit solutions in 2 dimensions, and after some attempts, he found the following function to be a solution. U of x and y is x to the 4/3 minus y to the 4/3. And that is easy to check, because u sub x is 4/3 times x to the 1/3. U sub y is minus y to the 1/3 minus 4/3 y to the 1/3. U sub xy is 0. Uxx is 4/9 x to the minus 2/3. And so ux squared, uxx, is 4 times 16 is 64/81 times x to the minus 2/3 times x to the 2/3 times 1. Yes? And similarly, uy squared, uyy is minus 64/81. Now this is in contrast to the harmonic functions. For harmonic functions, you have, for instance, x squared minus y squared as a solution. This solves Laplacian u equals 0. So this one solves infinity Laplacian u equal to 0. At least away from the origin. In the origin, the second derivatives blow up, and we don't know how to give a meaning to this differential equation. And this is what viscosity solutions try to do. First of all, they give us a notion of solution for equations that are not classically elliptic, that are degenerate elliptic. And secondly, they allow us to look at solutions that are not classical. So let me give some definitions. Now we're dealing with nonlinear elliptic equations. So I want to say when an equation is elliptic. Definition. An expression, a function depending on x, on u, on the gradient of u, and on second derivatives of u, that's equal to 0, for instance, minus Laplacian u, or minus the infinite Laplacian of u. We call that elliptic or degenerate elliptic. If for any x and omega, any u, any vector gradient u, the gradient of u, the variable for gradient u will be in Rn, so the x is also in Rn. X is in omega, in the domain omega. Q is in Rn. And the matrices x and y are in Sn. Those are symmetric matrices, n by n matrices. With x less or equal to y. It means that the eigenvalues of x are less or equal to the eigenvalues of y. Symmetric n by n matrices have real eigenvalues, so we can compare the eigenvalues. If this inequality, x less or equal to y, implies that for f we have the reverse inequality, f of x, u, q, and x is greater or equal to f of x, u, q, and y. So a simple example. We take f to be the trace of the matrix x, of the matrix D2U, minus the trace of D2U, minus the trace. The trace of a matrix is the sum of the eigenvalues. So if this matrix is smaller than that matrix, then the trace of x is smaller than the trace of y, and therefore minus the trace of x is greater or equal to minus the trace of y. This is elliptic. So minus Laplacian u equal to 0 is an elliptic equation. But Laplacian u equal to 0 is not an elliptic equation. That's a bit confusing. But there's a good reason for it. Okay. Well, let's look at another example. Let's look at the heat equation. U sub t minus Laplacian u equal to 0. For x and t in some space-time cylinder omega cross 0 t. Yes. And then this x and t is a variable in our n plus 1. So this as a function of n plus 1 variables satisfies a degenerate elliptic equation. Is degenerate elliptic because you can write f, also q here, the vector that contains all the derivatives with respect to x and t. This is a vector in Rn plus 1. And so the equation reads qn plus 1 minus sum over I equal 1 to n, and now the diagonal elements of the matrix of second derivatives only in direction x. There is no entry in direction t. The second derivative in direction t does not occur here, and therefore the summation goes only in this direction. So this is and this is the equation. It is independent of u sub tt. So it is almost like the Laplace operator, except that the coefficient in front of minus utt happens to be 0, so it is degenerate. And then we have a first order derivative. Okay. And yeah.
When is it called non-degenerate?
So non-degenerate is if you have strict inequality here, when you have strict inequality there, yeah. So then it is non-degenerate elliptic. Yeah. But since I will only talk about the degenerate equations, I did not bother to give the definition. Okay. Third example. Suppose we have a function that depends on u and the gradient of u, and it does not depend on second derivatives. Then it is degenerate elliptic. So, for instance, an equation like f of x equal to 0 is a degenerate elliptic differential equation, or u of x equal to sine x, or modulus of gradient u squared equal to 1. These are all degenerate elliptic equations in the sense of viscosity solutions. It's a bit confusing, huh? Okay. So now, so far I have defined ellipticity. Now I want to define viscosity solutions. U is a viscosity solution, a viscosity subsolution of f x u du d2u equal to 0 in x, or a viscosity solution of the equation f less or equal to 0 in x, viscosity subsolution, if u is upper semi-continuous and if f of x v dv d2v is less or equal to 0 for any smooth function v, smooth in the sense of C2, such that v minus u is minimal in x. We can think of it as v touches u from above in x. And correspondingly, u is a viscosity supersolution. Of f equal to 0 or a viscosity solution of f greater or equal to 0 if u is lower semi-continuous and f of x, let me call the function here w, dw, d2w is greater or equal to 0 for any smooth w such that u minus w is minimal, or such that w touches u from below. In x. And finally, u is a viscosity solution if and only if it is a viscosity subs and supersolution. And of course, I mean, the first question that one has is, are classical solutions viscosity solutions? And that is a theorem. Classical solutions. Are supersolutions. Are viscosity solutions. Now let me return to this example, or u of x and y equal x to the 4/3 minus y to the 4/3. This is a classical solution of minus the infinity Laplacian equal to 0. Whenever x is not equal to 0 and y is not equal to 0. So that is a viscosity solution. Now let's visualize this function along the x-axis. Y is equal to 0. Then it is x to the 4/3. Yes. This is x to the 4/3. To show that the function is a viscosity supersolution, we have to, no, a viscosity subsolution, we have to touch it from above with a C2 function. Now a C2 function that touches in this point, say, must grow at least quadratically. Yes. But when it grows quadratically, it behaves like this. And I can take 10,000 times a parabola, and it still gets below. I find no smooth C2 function that touches from above. So the set of functions for which I have to test this condition is empty. And this makes this function here, viscosity subsolution, at least when x is equal to 0. And in the opposite direction, so you have a saddle here. But you have the same kind of saddle here. You go up x to the 4/3, and in the direction that comes out of the plane, you go down minus y to the 3rd from this point. And you cannot touch with the smooth function from below. And so this way one can show that this is in fact a viscosity solution. Yes. I did not tell the full story. So in this point here, you have to check something. Here you can check with a smooth function from above. You can have a smooth function touching here. And in fact, along the line y equal to 0 and x non-zero, the gradient of u is pointing in direction of x. And so the second derivative with respect to the gradient of u is the second derivative with respect to x. And since this is a convex function, this second derivative is positive, minus the second derivative in the gradient of any function that lies above it is less or equal to 0. Yeah. And if you touch from below, you find no function that touches from below there. That is smooth. So this function is in fact a viscosity solution of this equation. Okay. I guess I'll leave this here. So we have learned that, well, there are some non-classical solutions that describe meaningful physical phenomena, and the notion of viscosity solution helps to explain them. Next point that I want to make is that solutions to degenerate elliptic equations can violate boundary conditions. And let me start with the first example. Consider u prime of x equal to 0 in the interval from 0 to 1, u at 0 equals 0, u at 1 equal to 1. Well, since we are looking for a constant function, it cannot be simultaneously 0 or 1, so it has to violate one of the boundary conditions. Yes. This cannot have a classical solution. There is no C1 solution. But we can instead study the problem minus epsilon times u double prime plus u prime equal to 0 in 0, 1. U at 0 equal to 0, u at 1 equal to 1. And this is a strongly elliptic equation because the coefficient in front of the second derivative is a constant. And of course this has a solution. I mean, an ordinary differential equation, so you start with trying e to the lambda x and so on, and when you calculate the solution has a unique solution, it turns out to be u epsilon of x is e to the x over epsilon minus 1 over e to the 1 over epsilon minus 1. And when you plot this function, so this has it as a unique solution. When you plot this function, it behaves like this. Now, u double prime and u prime have the same sign, since u prime should be positive if the solution goes from 0 to 1. U double prime should also be positive. It behaves like this. So this is u epsilon of x. And what you find out is that as epsilon goes to 0, the pointwise limit of u epsilon of x as epsilon goes to 0 is 0 if x is between 0 and 1, and it is 1 if x is equal to 1. So we have a classical solution, and when we send epsilon to 0, we get a function that develops a boundary layer, and in the limit it is a discontinuous function. Now this function is upper semi-continuous. Let me call this function u0 of x. It's upper semi-continuous, and it satisfies let's see, is it a viscosity subsolution of the limiting equation u prime equal to 0? For that to hold, we have to show that v prime is less or equal to 0 for any v that touches u from above. Yes. Is upper semi-continuous, so this u0 is this function here. And it takes this value up here. And it satisfies v prime of x less or equal to 0 for any smooth function v touching u0 from above. In a point x which is between 0 and 1, but not including 1. Because in the point 1, I can have a function, excuse me, oh, it's wrong. It is also not in 1, okay. In the open interval 0, 1. So here I can have a function going this way or a function going that way, function v touching it from above. Here I can have a function going up like this. Okay. So therefore it is a viscosity subsolution in the open interval 0, 1. And in a similar way, one can show well, to check if it is a viscosity supersolution, it has to be lower semi-continuous. So let's look at the lower semi-continuous version of U0, which is just, we drop this point down here. So the lower semi-continuous version of U0, which is the largest lower semi-continuous function lying below U0. Let me call this the lower semi-continuous hull. U0 substar of U0 is just U0, identically 1 in the closed interval from 0, 1. And satisfies W prime greater or equal to 0 for any W touching U0 from below in points 0 and 1 including. Because if we touch here from below, the W prime has to be greater or equal to 0. If we touch here, it has to be less or equal to 0. So the differential equation is satisfied in this inequality sense, in the right boundary point. And what we can conclude is that U0 star, which is a continuous function, is a viscosity solution of the limit problem after we send epsilon to 0. But of course, boundary conditions are violated often in the interval. But a boundary condition gets lost. Incidentally, remark. If we had started with the equation minus u prime equal to 0, u at 0 equal u is 0, u at 1 equal to 1, then minus epsilon u double prime minus u prime equal to 0 gives you a different family of solutions, namely something that converges to 1 almost everywhere and that has a boundary layer over here. U super epsilon of x. So then you get a different viscosity solution in the limit. So this tells us that the viscosity solutions of this equation with these boundary conditions are not necessarily the same as the viscosity solution of that equation. Multiplying an equation by -1 can lead to a different set of solutions. Another example in this direction, and that's a lengthy exercise, is you look at the equation u prime equal to 1 in the interval -1, 1, and you require that u at 0 and u at -1 is equal to u at +1 is equal to 0. Now, then you can have a solution Well, we know the slope has to be 1, so we can start with a solution that has slope 1, and then it has maybe slope -1, and then it has slope 1 again. The modulus of the slope is constant. So this is a weak solution. This is a solution that satisfies this equation almost everywhere, and the boundary condition. But you can also have a solution that satisfies this. And you can have one that goes all the way down, and you can have anything in between. Something like this. Now when you regularize this equation, minus epsilon u double prime plus, I think, maybe it's u prime squared here, equal to 1. What you find out is that you get a u epsilon that behaves like this. Gives you epsilon close to u equal to minus modulus x. When you have minus epsilon u double prime minus u prime squared equal to -1, so you take the equation u prime squared equal to 1, you multiply it with -1, you do the same thing, then you get this solution down here. And there are physical phenomena and modeling phase transitions where each time that you switch the sign of the derivative, you have a different phase of some material. And these viscosity solutions, they take care that you do not have too many switches between phases. And there's a physical phenomenon called Ostwald ripening. The material science, for which this is sort of a caricature of a model. And the viscosity solutions, they give us the physically meaningful solutions that two different phases of the material separate, and in the end one phase will be on one side, another phase will be on the other side, and the interface between these two phases will be minimal. Okay. Now we have seen boundary conditions are violated. So I want to define when the boundary conditions are satisfied in the viscosity sense. U is a viscosity solution of the boundary value problem f of x u du d2u equal to 0 in omega, a boundary term of u on the boundary of omega if it is a viscosity subsolution and a viscosity supersolution. So let me write here, it is a viscosity subsolution of this boundary value problem. If, first of all, it is upper semi-continuous, and if it is a viscosity solution of the equation f less or equal to 0 in omega, I mean the differential equation should be satisfied, and if the following is true, the minimum of f x u du d2u and bu, this is less or equal to 0 on the omega. in the viscosity sense.
What can be BU?
BU can be either Dirichlet condition, U equal to 0, or Neumann condition, the U by the N equal to 0. So here, BU is either U or BU is du by the exterior normal derivative. I don't know if, I never checked if also Robin is possible. I think it should also be possible. If you want to read this in detail, there is a long article by Crandall, Ishii, and Lyons called User's Guide for Viscosity Solution or so. It's a very long article, 70 pages or so. And there's one section on boundary conditions.
Sorry, do you assume that
Excuse me?
function is twice continuous?
What? F?
F and U.
F is continuous, yes.
But if F is less than 0,
Ah. No, we know when a function is less or equal to 0 in the viscosity sense. We touch it from above with some smooth function, and we check if that one is less or equal, if the expression is less or equal to 0 for that function. Yeah? So I...
Там другое множество касательных, оно резко меняется. Кто его знает?
So let me see again. This function u0 here. If it is a viscosity solution of the boundary value problem at x prime at x equal to 1, I mean the solution here violates the boundary condition in the classical sense. So u is not equal to 1, and any function that touches from above is not, and no, even the continuous version of u0 here. If I have a function that touches from above, it satisfies the boundary condition in the classical sense, yes.
In viscosity sense.
Excuse me?
In viscosity sense.
In the viscosity sense, yes.
Excuse me,
Yeah.
on the boundary, the second derivatives of u are understood
In the classical sense. The second derivatives are only taken for smooth test functions, right? So when I write that this is less than or equal to 0, I mean any function w that any function v that touches from below. When I plug v in here, then it satisfies this inequality. F touches from above.
That's a condition which is only tangent to the boundary or up to interior.
This is only on the boundary. For the in the interior, it's, this inequality must hold in this sense. I said f satisfies this inequality if this is the case. Yeah? And on the boundary, f also satisfies this inequality if this holds. So this, therefore, I wrote here in viscosity sense. Yes. Yeah. For viscosity super solutions, the signs are reversed. Yes. The minimum should be greater or equal. Now we have already seen that this function u0 identically to 0 is a viscosity solution in the interval. A classical viscosity solution in the interval of u prime equal to 0. And it satisfies the boundary condition at the left end, u equal to 0 in the classical sense. Yes. At the right end point, it satisfies also the boundary condition for super solutions. Yes. Where do we have it? Here. So at the right end point, it is a viscosity super solution of this equation, and therefore it satisfies the boundary condition in viscosity sense in the right end point. For viscosity subsolution, I need to know that any v touching from above in the right end point satisfies the limiting equation, in this case v prime less or equal to 0. And in fact, this is the case. If I have any smooth function touching here from above, v prime, it has to be less or equal to 0. Yes. So in those points where the classical boundary condition fails, the differential equation still holds. And then we are on the safe side. Okay, so I tried to convince you that maybe the concept of viscosity solutions can explain and give a meaning to degenerate effects in differential equations. In particular, the definition of viscosity solution is very delicate, and one needs this elasticity assumption is very important. When we have an equation and we have a solution for the equation, and when the equation is invariant with respect to u, and to the sign of u, we cannot just take the same equation for minus u and expect the class of viscosity solutions to remain invariant. So multiplying an equation with -1 is a dangerous thing, but also multiplication of f equal to 0 with a non-negative factor can lead to different solutions. And as an example, consider minus u double prime equal to 1 in the interval from -1 to 1, and u at plus or minus 1 equal to 0. And that has, of course, a solution that is a parabola. U of x 1/2 minus x squared over 2 as a solution. Now I multiply the equation with u prime squared minus u prime squared u double prime. This is the infinite Laplacian, huh? Second derivative multiplied with a gradient squared, equal to u prime squared.
There is a full Laplacian, no?
It is also for Laplacian, yes. Happens to coincide with the infinity Laplacian, yes. Also for Laplacian, yes, that's right. in minus 1, 1, and u at plus minus 1 equal to 1 has a family.
0.
0, sorry, yes. Has a family of solutions, and this family of solutions is constant in some interval, and then it starts as a parabola and goes down to 0. U alpha of x, which is 1/2 times 1 minus alpha squared for modulus of x less than alpha, and 1/2 times 1 minus alpha squared minus 1/2 times x minus alpha squared for x greater or equal to alpha, and alpha between 0 and 1. As a family of C1 viscosity solutions.
Alpha 0 is also okay.
What?
Alpha 0 is also okay.
0 is also, yes. Yes. And alpha equal to 1, I guess, also. No, alpha equal to 1, no. Yes, alpha equal to 1 also, yes. So you can function u identically 0 is also. And here it is C1, it is not C2, so it's not a classical solution, but it is a viscosity solution. Another example. Where the boundary condition gets lost in the limit. Is the following. Consider a rectangle, x, y, and we look at the equation minus epsilon times u y minus u x plus u sub y equal to 0 in this rectangle, D. U is a given function g on the boundary of D. Now this is an elliptic equation. We can prescribe directly data here, 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 here. And let's call the solution u epsilon, depending on this parameter epsilon. Yes. When epsilon goes to 0, the equation becomes the heat equation. U sub y minus uxx equal to 0. And we identify y with the time axis. And for the heat equation, we know that we can prescribe initial conditions, we can prescribe boundary conditions, but we cannot prescribe final conditions in general. So the limit of the u epsilons satisfies the heat equation. And it satisfies the heat equation in the classical sense at the top of this rectangle. But violates the boundary condition at y equal capital T in general. I mean, it may be that we chose the G in such a fortunate way that we get also that the boundary condition is satisfied. Huh? But this is another instance where you have a degenerate elliptic equation. Any parabolic equation is elliptic. People working on evolution equations do not like to hear this, but so it's just degenerate elliptic. And then what you have is that the boundary condition is satisfied in the viscosity sense, which means that the differential equation holds. So now let me come to a different subject, and that is the P Laplace operator. And let me study the P Laplace equation. So we look at the Dirichlet problem. Minus the P Laplacian of u. Now what is this? This is minus the divergence of gradient u to the p minus 2 gradient u equal to f of x in omega and u equal to some function g of x on the boundary of omega. For p between 1 and infinity. It has a unique solution under reasonable assumptions on f and g. And that solution minimizes an energy EP of v, which is the integral over omega 1 over p gradient v to the p minus f times v dx on the set of functions v that can be written as a function g plus a function in w1p with 0 boundary values. Now, if this functional, I mean, this is a convex functional, a strictly convex functional, so it has a unique minimizer. And when you write down the Euler-Lagrange equation for the minimizer, you get this as a differential equation. Now, who does not know what the Euler-Lagrange equation is? Everybody does. Okay, and I don't need to do it here. Okay. So it is a weak solution. And one knows that weak solutions are viscosity solutions. So there's another theorem. Weak solutions of this problem are viscosity solutions. But let me differentiate the P Laplacian out. So that is, if I take the divergence over to the gradient, I get the Laplacian, gradient u to the p minus 2 times Laplacian. And if I take the divergence over to this one, d by dxi of that one, that gives me a p minus 2 gradient u to the p minus 4, and then we have u sub xi, u sub xi, xj, u sub xj. So that's again the infinity Laplacian operator. So we can write it as minus gradient u to the p minus 4 Laplacian u times gradient u squared plus p minus 2 times the infinity Laplacian of u. Or minus gradient u to the power p minus 2 Laplacian u plus p minus 2 times u sub nu, where nu is the direction, the outward normal to a level set of u. So I take the direction of steepest ascent, I reverse it, and I normalize it, and I get this.
Why is it needed to reverse?
Excuse me?
Why is it needed to reverse?
It's not needed, no, but I just like to think of it this way. Yes. Second exterior normal derivative. Yes. Now the Laplacian, I claim, can also be written as a second derivative orthogonal to a level set of u plus something else. And this something else is n minus 1 times h times du by du, where h is the mean curvature of a level set. And the point x, and du by du is the exterior normal derivative. Now, in polar coordinates, if we have a function that depends only on the radius, and for radially decreasing functions, we can write a Laplacian as second derivative of u with respect to r plus n minus 1 over r times du by dr. This is the same kind of decomposition. It is the second derivative in normal direction to a level set plus n minus 1 times the curvature term. The mean curvature of a sphere is 1 over r if the sphere has radius r times du by dr. And in fact, I want to convince you of this formula. So we consider the divergence of gradient u over the modulus of gradient u minus gradient u over the modulus of gradient u. So that's minus Laplacian u over the modulus of gradient u plus, and here we have again du, d2u, du divided by gradient u to the power 3. And this here, this tells us how the normal vector changes along a level surface of u, and it also tells us how the tangent vector changes along the level surface of u. This is the mean curvature. So this is n minus 1 times h. This is u double nu divided by gradient u and minus Laplacian u. And when you rearrange this formula, you get that one there. And I call, and if you do the same for the P Laplacian here, what you get is minus gradient u to the p minus 2. And since the Laplacian contains a u double nu, the u double nu I put over here, I have p minus 1 u double nu plus n minus 1 times h times u sub nu. And let me write that again. Minus p Laplacian u is minus gradient u to the p minus 2, p minus 1, u double nu plus n minus 1 times h times u sub nu. And I call this the P Laplacian in intrinsic coordinates. I mean, I look at a map of u and I say, okay, the first second derivative that I take will be normal to a level surface, and then I take all the other ones orthogonal to it. Well, what happens with this equation when p goes to infinity? Or when p goes to 1. And let me do this for a special case. That f is identically 1, g is identically 0. Then we have the p torsion problem. And omega is the ball of radius capital R centered at 0. Then we have to write the P Laplacian in terms of polar coordinates. And an easy way to derive it is to go through the weak formulation. The weak formulation tells us that the integral, now we integrate the radius from 0 to r and over the unit sphere. Omega 1 is the unit ball, dB1. Then we have here gradient u to the p minus 2, gradient u, gradient phi minus phi. And the dx becomes d omega, integrating over the boundary of the unit sphere. And then we integrate over the radius r to the n minus 1 dr. And since u and the test function phi are only supposed to depend, well, okay, first of all, you have to see that the solutions of this problem on a ball, they are radial and radially decreasing. And one way to see this is by seeing that they are unique, because if they are not unique, you could rotate them, you could get another one. So they must be radial. And then it's also easy to see that they are radially decreasing. You solve the corresponding ordinary differential equation. Well, here we integrate first over the angle, then we get the volume of the unit ball, omega n, and integrate from 0 to r, modulus of ur to the p minus 2, u sub r, phi sub r minus phi, r to the n minus 1 dr. Where omega n is the surface area of B1 in Rn. And that can be given as omega n is alpha n mal alpha n times alpha n. Alpha n is the volume of B1 of 0 in Rn. And that is explicitly known as pi to the power n over 2 divided by the gamma function in n over 2 plus 1. Okay, and the functions phi that we take for as test functions, they have to vanish on the boundary of the disk, and they must be radial, and they should be smooth functions. So the functions phi are supposed to be, I don't know, in C infinity from 0 to 1, from 0 to r. Phi prime in 0 should be 0, and phi in capital R should be equal to 0. So then you integrate by parts. Here, you integrate by parts. You get that the integral of 0 to capital R minus d by dr. And here we have u sub r to the p minus 2, u sub r times r to the n minus 1 times phi. This should be equal to r to the n minus 1 times phi. 0 to r. And now we have the ODE that we have to solve for u. Minus ur to the p minus 1 ur times r to the n minus 1. This sub r is equal to r to the n minus 1. Whoops.
Modulus in the power of
P minus 2, thank you. Yes. Okay. And now this is an exercise in calculus to calculate the solutions. I don't know if I should do all the calculations in detail. No, it's not needed. Okay. So we finally, you integrate and you find out u of r is equal to u of 0 times 1 minus little r over capital R to the power q, where q is p over p minus 1. And that's a number between what?
But U0 should be unique.
And U0 is unique, yes. This is yes. So let me first write it. This one is between 1 and infinity. U of 0. This is n over q times r over n to the power q. So there we have a strange parameter. And let's see. The limit p to infinity is somewhat easier. When p goes to infinity, q goes to 1. So we have here u of 0 is equal to n over 1 times r over n, so that's r. So up tends to a function u infinity with u infinity at 0 equal to r, and u infinity at x is just r minus the modulus of x. This is a cone. Infinity, yes. You know that mathematician says A, he means B, and correct is C. Yes. But he writes D. Now what happens as p goes to 1? As p goes to 1, q goes to infinity. So when q goes to infinity, n over q goes to 0, which is nice. R over n, what happens? Now if the capital R is less than n, we have a number here which is smaller than 1. So as q goes to infinity, this expression goes to 0. And even when r is equal to n. If r is less or equal to n, up goes to 0 uniformly. If r is bigger than n, up goes to plus infinity. Locally uniformly. So when p goes to 1, the size of the domain plays a role. When p goes to infinity, it does not play such a role. And let me remark, up are radial, A, because they are unique, and the up are radially decreasing by a variational argument. Suppose you have a function that is not decreasing, radially decreasing. Suppose this is v of r. Then you can replace it by a function v tilde of r. If up is not radially decreasing, replace by up tilde, and this is, whoops, the maximum up tilde of r, the maximum of up of s for all s in the interval from 0, no, for all s in the interval from little r to capital R. Yeah. What happens? So you replace it here by something constant, for instance, and this will increase this term with a minus sign, it decreases this term. And also in a place where the gradient of u was non-zero, it is replaced by a place where the gradient of u is equal to 0. So this will decrease the energy. Will decrease. EP of up tilde will be less than EP of up, and that's a contradiction because up was a minimizer of the energy. Yes? All right. Let's take another look at these equations. They are not classical solutions, unless p is equal to 2.
It's less oracle.
But also for p bigger than 2.
Yeah.
Yeah.
In diagonal transform.
So up of r are not classical. Not even for p bigger than 2, because the second derivative up differentiated twice behaves like r to the q minus 2, and then becomes singular at the origin. So this blows up. Q less than 2. And the first derivative is Hölder continuous, I think. Yeah, so they are still C1 alpha. All right.
C1 alpha
So they
for P Laplacian is general result.
is a general result, yes. That's what we can expect. We cannot expect anything more. Yeah. So I think I will stop here with the first part of the lectures, and next time I will try to show you that at least this cone that we got here is a viscosity solution of the limiting equation.